Welcome to the training for Mechanical Science Fundamentals, Compressed Air Systems. The average time to complete this training is estimated to be 20 minutes. After you have completed this portion of training, you will be directed to the next training lesson in the series for further instructions. These are the objectives for this course. The purpose of a compressed air system is to provide a continuous supply of compressed air. These systems are also called pneumatic systems. The compressed air can be delivered at several different pressures by using pressure control valves. The source of compressed air can be compressor or cylinders or bottles. Compressed air systems supply instrumentation and control systems, breathing air systems, and are used to support the operation of many processes and portable tools. Compressor systems consist of one or more air compressors. Normally, a single compressor can supply one or more systems with compressed air. One of the most important uses of compressed air is for indication and control of process and support systems at LWO. For example, the numerous heating, ventilation, and air conditioning HVAC systems are controlled almost exclusively by air-operated actuators. These systems would not function without a dependable supply of clean compressed air at the proper pressure. Compressed air systems which support vital operations have redundant compressors. The number of compressors installed is greater than required for 100% capacity. The redundant compressors allow one of the compressors to be taken out of service for maintenance without affecting system operation. The redundant compressors also have redundant power supplies, so the loss of one power source will not cripple the system. Intake air filters are the first component in any compressed air system. These filters remove most of the dirt and other solid contaminants. Dust, for example, can cause sticking valves, scored cylinders, and excessive wear. These filters may be the dry or wet type depending on the compressor manufacturer and the application. The amount of air handle and the type of compressor also determine the type of filter used with a compressor. Dry fibers are made in different shapes and configurations. Most of them have a felt or cotton material packed into a wire screen or other retaining element. Other dry filters use replaceable or cartridge elements. The reciprocating air compressor is the most common design used in industry today. It uses a cylinder and piston arrangement to increase the pressure of system air. The construction of a reciprocating air compressor is similar to that of a refrigeration compressor. As a piston moves down, it draws air through the intake valve against spring pressure and fills the cylinder volume. As a piston starts a compression stroke, the intake valve spring closes the valve. As the piston rises, it compresses the air in the cylinder. When the piston has nearly completed the compression stroke, the air pressure is high enough to force the discharge valve open against spring pressure. Air discharge from the cylinder at this point is at the discharge pressure of the compressor. If higher compression is needed, additional cylinders are added with each cylinder being smaller than the previous one. Similar to a rotary vane pump, the rotary slide vane air compressor has vanes that slide radially in a slotted rotor which is mounted off-center in a cylinder. Centrifugal force carries the sliding vanes against the cylinder casing, where the vanes form a number of cells in the space between the casing and rotor. The size of each cell is reduced as the rotor turns and the vanes approach the discharge port. The reduction in size compresses the air. Similar in concept to a gear-type pump, the rotary lobe air compressor features two lobe-type rotors mounted in a case. The lobes are gear-driven at close clearance, but without metal-to-metal contact. The suction to the unit is located where the cavity made by the lobes is largest. As the lobes rotate, air is trapped between the lobe and the casing. The most common application of a rotary lobe compressor is on a diesel engine. The rotary lobe compressor can deliver the high airflow rate required by a diesel. Similar in design to the rotary screw pump, the rotary screw compressor combines compactness with a more constant pressure output than a piston compressor. Air is trapped between the casing and the grooves of the rotor and moved from suction to discharge. As the air moves towards the discharge end of the screw, the area in the screw groove decreases, causing the pressure to increase. One screw is driven by the prime mover, the rotor. The other screw, the idler, is driven off a gear off the rotor. The centrifugal compressor is very similar to the centrifugal compressor for refrigeration. It has adjustable vanes on the inlet that regulate flow into the impeller. A centrifugal air compressor may have several stages, just like a centrifugal pump can. The result would be the same, a higher pressure would be produced. Centrifugal compressors are most frequently used for medium volume and medium pressure air delivery. One advantage of a centrifugal compressor is the smooth discharge of the compressed air. A common application for centrifugal compressors is in turbochargers. A centrifugal compressor has adjustable vanes on the inlet that regulate flow into the impeller. The impeller is driven at a high rate of speed by a prime mover through gearing. As air is drawn into the eye of the impeller, it is slung outward and collected by the volute. The increasing volume of the volute takes the high velocity and converts it to pressure. When air is compressed, both its pressure and temperature increase. In a 2 or more stage air compressor, we can improve the performance of the second stage by cooling the air leaving the first stage. By supplying the second stage with cooler air, we get a lower second stage discharge temperature. This lower final discharge temperature means that the compressor air will lose less pressure as it cools to room temperature, since it experiences a smaller temperature drop. Air is drawn into the first stage cylinder. As the first stage piston moves upward, it compresses the air, opening the discharge valve, coming out at approximately 25 pounds per square inch. The air has picked up the heat from compression, so it is routed to the intercooler, which reduces the temperature and removes the heat of compression. The intercooler is cooled by process water. After leaving the intercooler, it goes to the second stage of the compressor, where the air exits the second stage at approximately 120 pounds per square inch and goes to another cooler called the aftercooler. Cooling the air after final compression reduces the volume of the air and makes it easier to remove moisture. Aftercoolers and moisture separators are used to remove moisture and oil vapors. We typically use water-cooled, as ambient air cannot lower the temperature enough to condense all of the water vapor. The aftercooler and separator, placed at the discharge of a compressor, condense and remove about 70% of the water vapor contained in the compressed air. This results in reducing the load on the air dryer. A receiver is a storage location for compressed air. A receiver must be the correct size for the volume of air in the system. This allows for the receiver to balance continuous compressor capacity against much larger peak airflow demands that occur. This minimizes cycling the air compressor. Air receivers dampen pulsations or pressure waves that are common with reciprocating compressors. Air receivers also allow a place for moisture to collect that may be carried over from the air dryers. For this reason, many air receivers are equipped with drain traps to remove any collected water. During short periods of peak flow demand that exceed compressor capacity, air stored in the lines in the air receiver will keep the overall system pressure from dropping too low. Rather than have multiple compressors providing different pressures, the system is set up to provide the highest pressure needed, and then the pressure is reduced for those components or systems requiring less. Reducing stations are located throughout the distribution header. Each pressure control valve normally has an inlet isolation valve, outlet isolation valve, and a bypass valve. A reducing station may consist of more than one pressure control valve in parallel to have a backup in the case that one of them fails. The branch headers may also contain pressure control valves set to deliver needed pressures required for various components. Air headers are runs of piping that carry the compressed air to different systems. They contain valves, flow elements, and indications. On multi-compressor systems, there is a common discharge header. The header combines the discharge of all the compressors before it is filtered, dried, and stored. The main supply header, which is usually after the receivers or filters, distribute the compressed air to the branch headers. The branch headers distribute the air to various systems. The branch headers will normally contain the pressure control valves located at reducing stations. Pressure control valves reduce the pressure of the compressed air to the pressure required by the system supplied. You should become familiar with the order and relative location of the air system components. Air dryers are another means of removing moisture. Air dryers remove water vapor from air without condensing the water. Air dryers are normally used for instrument air systems. Desiccant or absorption air dryers are the most commonly used for instrument air systems. Desiccants are chemicals that readily take up and retain moisture on their surface. Most systems have two towers with one tower in service at a time. When that tower's desiccant becomes saturated, airflow is switched to the standby tower, and the saturated tower is regenerated by heating and reversing the airflow to remove the collected moisture and dry the tower. Cycle times between towers usually range between 4 and 8 hours. When the compressor is running fully loaded, it is compressing air and discharging the compressed air to the system at full capacity. When system demands decrease and the receivers are fully charged, full flow is not needed. A pressure signal from the receiver actuates an unloader. The unloader is a device that holds open the suction valve on the compressor cylinder or cylinders that prevents the cylinder from compressing the air. When the compressor is running fully unloaded, it is not compressing air. It is still running at the same speed as when it was fully loaded, but less compressed air is discharged to the system. This allows a compressor to run continuously without having to shut down during low loads and start up during peak loads. Gas bottle systems are used to provide a continuous supply of specialty gas such as nitrogen, carbon dioxide, oxygen, and argon. Compressed gas bottle systems contain a manifold for connecting several gas cylinders. The number of cylinders connected to a manifold depends on the quantity of gas required by the system being supplied. If a large quantity of gas is required, more cylinders must be connected to the manifold. The manifold typically has a pressure regulator to reduce the pressure to the pressure required by the system. If more than one system is supplied by the compressed gas bottle system, additional pressure control valves can be placed downstream of the regulator. Gas bottles should be handled very carefully. Keep bottles away from heat and flame, as this could cause explosive gases to explode, or heating the cylinder to lift the relief plug and/or rupture the cylinder. Shut the cylinder valve and secure the cap when the cylinder is disconnected. Never lift cylinders by the protective cap. Store bottles upright and always clamp or chain them in place to keep them from falling or being knocked over. Always transport cylinders in secured and appropriate vehicles. Here we see a clip from the show Mythbusters where they're knocking the valve off a gas cylinder to see if it will actually blow through a concrete wall. Knocking the valve off the cylinder basically turns it into a rocket, allowing the gas to escape rapidly and propel the bottle towards a brick wall. They discovered that not only did it blow through the wall, it also damaged the wall behind it. This is a good reminder on why it is important to keep the cap on at all times when the cylinder is not in use. Oil introduced in an air compressor can be compressed to the point where detonation occurs, in the same way that detonation occurs in a diesel engine. This detonation can cause equipment damage and personal injury. We know that if we compress air, it will heat up. In the opposite case, when a gas expands, the temperature will drop. If a compressed air line is suddenly depressurized, there is potential to form ice crystals at the point of the pressure drop. Ice formation may also occur when opening large air valves rapidly and could cause them to become blocked. The higher the air pressure and the higher the air moisture content, the more likely ice formation will be. Small leaks or breaks in the compressed air system can cause minute particles to be blown at extremely high speeds. Always wear appropriate PPE when working in the vicinity of any compressed air system. Compressors can make an exceptional amount of noise while running. In the vicinity of the compressor, the noise of the compressor in addition to the drain valves lifting creates enough noise to require hearing protection. The area around the compressor should normally be posted as a hearing protection zone. The compressors, air dryers, and most piping are hot due to the heat from compression. Care should be taken to avoid contact. Approved gloves should be worn to protect against burns and pinch points. Valves should be operated slowly to minimize pressure swings in the system that may damage other components.